Good afternoon, everyone. Today we'll be covering 3.4, maybe getting to 3.5 as well. This is on measures of position. And we're going to start where we left out last, which was with the bell-shaped distribution. Remember with the empirical rule? So we're going to deal with the bell-shaped distribution. But we can talk about position in terms of where certain data fall in that distribution. And something called a z-score. So I'm going to start with a problem, and this is in 3.4. They do explain, this is bell-shaped, so it's section 3.4, page 171, and it's number 8. It's titled Men versus Women, and they start by saying the average 20 to 29-year-old the average 20 to 29-year-old man is 69.6 inches tall with a standard deviation of 3. All right, so I'm going to write that down. For the average, this is for a population. I can use mu, correct? 69.6 inches. So there's the average. All right. The standard deviation, 3 inches. So I'll just put SD for standard deviation. They also say the average 20 to 29-year-old woman is 64.1 inches tall with a standard deviation of 3.8. All right, so I'll go over here. 64.1, standard deviation 3.8. That's for women. And the question they're asking in number 8, in these bell-shaped distributions, they're both bell-shaped, who is relatively taller, a 67-inch man or a 62-inch woman? So that's the question we're going to answer. Who is relatively taller? A 67-inch tall man or a 60-inch tall woman. And they're talking about the height there. Who is taller relative to their population? That's the question. Okay, well, they're both bell-shaped distributions. So we can make a bell for the men. We can make a bell for the women. And then we'll just look in the bell curve in this distribution. We'll see which one's further to the right side, right? Whoever's higher up this scale, right, is going to win this contest. Now, if it's too close to call, no worries. We'll go to a math formula. All right? We'll use a math formula. But I think it's good to first just look at these distributions. So, and you did a great job building these on your last test. So I'm going to go ahead and just build a bell for men. I'll just put men in here. Put a tick right in the middle. A 1, 2, 3, and a 1, 2, 3. What's right in the middle?
69.6.
69.6. For me, right? Now remember, for this, I have to add this. All right, what's 69.6 plus 3?
72.6.
Maybe I won't fill out every tick mark, but I'll fill out a few. I'm going to go 2 standard deviations above the mean. That would be
75.
75.6. This time I won't label the third one. I think I'll just label these 2. Just get a picture going. Pictures help us in stats. Help us understand this stuff. All right, I'll subtract 2. Subtract 3 from this, I get 66.6. Subtract another 3, I get 63.6. And this is in terms of height, so that's 5 feet, 3.6 inches tall.
Next one is 666.
Yeah. Right. All so there's the distribution of men. Women? Let's build one for the women. Okay, this is in terms of height. 1, 2, 3. Remember that third tick mark will be right where this is. Now, 64.1 for the middle.
Okay, so.
All right, feel free to use a calculator to help you out here.
67.9.
67.9. Now we got to add 3.8 to that.
So that's 9 plus 87.
71.7.
Yeah.
I would agree. Now for these two, I have to subtract 3.8. Feel free to use that calculator if you want to check it. Because I know you got a 3.8 in there.
60.3.
Oh, 60.3 for this one.
56.5.
And 2 standard deviations below the mean. We're talking about a height that is, what was that?
56.5.
56.5. Looks good. Looks good, right? Distribution of women, distribution of men. Okay, we can come back to this question now, huh? Right? Who's further up that way? True? Relative to the population. I'll use the yellow chalk.
So when
When
you
you get this out, we're just going to see who's further to the right. All right, 67-inch man. Let's make a mark in there. Where would that be about? What about here?
Mm-hmm.
There he is. I'm going to agree right around there?
Yeah.
Ballpark. How about the 62-inch woman? 60.3, 64.1.
Yeah.
Somewhere in here, ballpark. So right now, when do you agree it's too close to call?
Yeah.
From my picture, from me just making an image, it looks like it's too close for me to call, and we're going to have to go to a math formula. No problem. The math formula is going to tell us the answer. And what we're going to do, everyone, we're going to find something called a z-score. A z-score will give us the position of those data values in the bell-shaped distributions. How about that? It'll be a score. And you go, what does it represent? All right, the z-score, you might get a number like 1.5 or 2.3. It could be negative. But what it represents is how many standard deviations that data value is above or below the mean. That's what that z-score is going to represent. I'll say that a few times so you can copy it. We're going to calculate a z-score. You go, what's it going to represent? It's going to represent how many standard deviations above or below the mean that data value will be. By being below the mean, it's going to come out as a negative z-score. And by being above the mean, it's going to come out as a positive z-score. Okay? And so I'm going to go in here. You know, where's the math formula? Oh, I'll show you. I'll show it to you. But before I do, I want you to get a sense of what's the z-score going to be?
Relative.
Yeah, it's going to be a value, and it's going to tell us how many standard deviations above or below the mean that data value is represented by. All right. So in our pictures, everyone still got these pictures in your notes? These are x values. All these. Those are all x's right there. And see these? The 56.5 and the 60.1? Those we can refer to as the x values. They're x values. All right? Data values. Well, underneath it, let's write out z. Here, let's put a z. Everyone, right at the mean, in the middle of the bell, z is equal to 0. And at this first tick mark, z is equal to 1. And at this one, z is equal to 2. And at this one, z is equal to 3. How easy is that? These are z-scores. Guess what z is over here, though?
Negative 1.
Negative 1. See, on this side, negative z-scores. Negative 2. And at this location right there, negative 3. So I think we all agree, both of these individuals have negative z-scores, correct? Yeah, very good. They both have negative z-scores relative to their populations. Hey, can you have a z-score of like 5? Sure. Like, does anybody know Shaq from basketball? Maybe he's up at 4.2 or something. I mean, there's some outliers well beyond what we have here. But remember this? 99.7% of the data's in here within 3 standard deviations of the mean, but there are some that are way out there. You have higher z-scores. Okay. So over here, I'm going to do it again. What's z right there? 0, 1, 2. Throughout this whole course, you'll know what z-scores are. You go, oh, they're positive or negative numbers, usually between -3 and 3. We don't have decimals. All right.
They usually say up to 2 standard deviation is natural. Anything beyond that is abnormal.
That's right.
So is that what they use, the z-score or the
That's right. You'll use a z-score to determine it.
Okay.
That was good. So he's just talking about, like, in this world, sometimes we think of things that are kind of rare or unusual. And so we can, for our course, you want to just, for one number for our course, we'll just say anything under 5% chance we can consider unusual. Does that sound good? If there's like something less than a 5% chance. Maybe there was less than a 5% chance that we'd get no snow today. We're like, oh, well. They kept telling us all the snow we're getting, right? I'm looking out and I don't see anything. So maybe it was like a little unusual after all these predictions we heard. Cool. All right, so what is the formula for calculating z? I'm going to put it right over here. Z is equal to, I'm going to put it in words first. Z-score equals your data value. I'm going to put it with words first. The data, like that data value, the number given, minus the mean divided by the standard deviation. But that's with words. You could say the mean of the statistic and the standard deviation of the statistic if you want to add stuff. That's with words. So it's data value minus mean over the standard deviation. Let's put it with symbols. Let's start it with samples. What would that be with samples?
X of I.
X minus X with a
Bar.
bar on top all over the letter S. Cool?
Aren't you doing it for, oh, sample, sorry.
That's sample. Now we can write it for a population. And what would this formula look like if it was a population? All right, here's Z. X minus, what was mean?
Mu.
Mu.
Over
And
sigma.
then this funny lowercase sigma.
Sigma.
There you go. These are on the formula sheet. So if you're stressing, I'm going to forget that, you can look it up on the formula sheet. But that's this math formula for calculating Z. I do want to point out, this only deals with what kind of distribution.
Bell-shaped.
Yeah. We're not finding z-scores if the data's skewed. Skewed left or skewed right, okay? We won't even mention z-scores. We'll do something else to find a position. Cool? All right, are you ready? This is what you and I are going to do.